So here's from the IB syllabus what they expect you to know about sound, you guys. And the main thing with sound that we're going to be talking about is standing waves and kind of what they are and how they work, and this thing known as the Doppler effect. So that's what I want to talk about today. So what is sound? It's a wave. Can you be more specific? Longitudinal wave. What creates it? Vibrations. Okay, so a longitudinal wave created by a vibrating object. That is what sound is. And it is a mechanical wave, which means what? What does it mean for something to be mechanical? It can't go through a vacuum. It has to travel through a medium. That's what sound is. What are some of the vibrating things that produce sound? Think about that for a second. Vocal cords, your vocal cords, speakers, drums, the heads of guitars, whatever. It has something that is vibrating is what is the source of a sound wave. And ultimately, the vibrating object creates regions of high and low pressure that are oscillating longitudinally through the medium so that the sound wave is propagated. Another picture just to remind you of the difference between transverse and longitudinal waves. Sound is a classic example of a longitudinal wave. And if, again, this top picture is, imagine each of these little black dots being an air molecule. Each little air molecule is oscillating with simple harmonic motion in a longitudinal direction. And what that does is it creates area of high pressure, what we call compressions, and areas of low pressure, what we call rarefactions. So that's really all that picture is. How fast does sound go? Or do you have a question, Rex?
Well, you know, generally, to some extent, on things.
All right, so speed of sound. Roughly, the speed of sound is taken to be 343 meters per second at sea level and 20 degrees Celsius through the air. That's, I think, in the realm of 700 miles an hour, somewhere more or less. Yeah. But that's very specific. Different factors can affect the speed of sound. The material it's traveling through, the temperature of that material, the pressure, those things all change the speed at which sound travels. Usually we'll talk about 343, or sometimes in IB questions they'll say use 330 meters per second. But recognize that the speed of sound can vary depending on the material it's traveling through. And here are some examples. Again, air 343. When the air gets colder, sound travels more slowly. The hotter the air, the sound will travel faster through it. But other gases, it travels much faster. Notice that in solids, it travels quite fast. Okay, and this is, you know, speed of sound. To think about whales when they go underwater and they do their sounds, they can cause their sound goes a lot faster and a lot farther underwater than it would if they were making those sounds in the air. Okay, so what wave property is it that we experience as volume? The amplitude of the wave. The amplitude of a sound wave is the thing that we recognize as volume. Okay, and amplitude is also in waves, in mechanical waves, amplitude also deals with the energy that's transferred. So remember that the energy is proportional to the amplitude squared, and for us in sound, it's the amplitude of the wave that does volume. And basically what we mean when we say an amplitude of a sound wave, we're talking about greater differences in the pressure from the high to the low pressure. And we've created a scale to measure volumes. It's called the decibel scale or decibel scale. You don't need to memorize it. You don't need to really know much about it, but I'll just show you some numbers on it. It is a logarithmic scale. And so when things, you know, the decibel level gets really high, you get up to the threshold of pain at 120 decibels, you know, big rock concert, seeing the Who inside somewhere, it's going to be along the same lines as the threshold of pain where you start doing damage to your ears. So amplitude is volume. Therefore, if amplitude is volume, what is it that causes a change in pitch or a change in tone of sound waves? The frequency. It's the frequency of the sound wave that we experience as different tones and different pitches. And you can vary the frequency in a couple different ways. You can vary the frequency by varying the source, the vibrating object that creates the sound waves. If it vibrates with a different frequency, we get different sound waves. And you can also move the source. If you have a source that is putting out a constant source of sound, and that source is moving relative to an observer, the pitch will change, and that is the Doppler effect. Okay, that is the Doppler effect, which we'll get into more specifics here in just a sec. So the Doppler effect, you can see it visually kind of like this. That top picture, imagine there's a fire truck sitting there, its sirens are on, it's sending out sound waves in all directions. If the fire truck is standing still and the observers are standing still, all observers will hear the same tone because they'll be experiencing waves with the same frequency and same wavelength. However, if the fire truck is moving in this bottom picture from left to right, notice that it's moving along with the sound waves in front of it. So it's producing sound waves that are actually closer together, and it's leaving behind the sound waves that it's driving away from. So it creates different frequency waves in both directions. The person in front's going to hear higher frequency waves. They'll sound like higher pitch than when the truck was standing still. And the person behind the fire truck, from where the fire truck is leaving, will experience lower frequency sound waves or a lower pitch. If you've ever paid attention to like a police car driving by you or NASCAR races, you've heard this before. Because I'm not a big NASCAR fan, but if you're watching NASCAR on TV or in real life, I hear it's pretty intense. But think about it, the cars coming by, two things happen. The volume gets louder and then quieter, right? But the tone of the car's engine also changes. It's like when they go by. It goes from high pitch to low pitch, and that's the Doppler effect. Okay? It's an actual physical change in the frequency of the waves due to the motion of the source. The Doppler effect can also happen when the observer is moving and the source is stationary. Okay, so if you're watching this at home, check out these websites because they're pretty good. But I'm going to pause you if you're watching at home because we're going to explore them here. Okay, so here are your Doppler equations. They're pretty straightforward, and this is what you'll see in your data booklet. You've got one equation for a moving source, and you've got one equation for a moving observer. Both of these equations tell you the new frequency, or the altered frequency that happens because either the source or the observer is moving. Notice that each equation has a plus or minus symbol in it. Oh, that's not what I wanted to do. Plus or minus symbol there, plus or minus symbol there. You have to decide, is it plus or is it minus? And here's how I do it. I think this makes most sense. You guys were just able to tell me when a source is moving towards an observer, the frequency is going to increase, right? So that's your first step in solving these problems. Oh, I know I'm going to have to get a bigger frequency. So in this case, since this factor is on the bottom of a fraction, it needs to be smaller, so I'll be subtracting in that case. Does that make sense? Many of you have checked out at this point, but you can always check back to the video and see what I just said. Okay, so you have to decide, is the frequency supposed to increase or decrease in that particular situation, and that tells you whether you add or subtract the velocity of the source and the velocity of the wave. Okay? One other thing that I want you to notice is that when the source is moving or when the observer is moving, the frequency will always change. We talk about frequency when we talk about Doppler effect. The wavelength doesn't always change. Okay? The wavelength does not. If the source is moving, the observer will experience a different wavelength. But if the observer is moving through the waves, the observer will still experience the same wavelength as the source has, but it'll experience a different frequency because it's moving through. It'll appear that the waves are moving faster because of the velocity of the observer. So wavelength is kind of obscure. Sometimes wavelength changes, sometimes it doesn't in the Doppler effect. And it does change for a moving source. It does not change for a moving observer. The frequency of the waves, however, always changes, and it can be solved using these equations. Okay? Practice problem? Let's give it a shot. Okay, so the Doppler effect works with light as well, but the equation is much, much simpler with light because usually we're talking about speeds that are much slower than the speed of light. So it simplifies to this equation, which is in your equation book. The change in frequency of a light wave is equal to the speed of the source, or the observer, divided by the speed of light times the frequency of that light when it's at rest. Okay? So this is the Doppler equation for light. Again, it only works when the speed of the object or the speed of the observer is much, much, much slower than the speed of light, which is almost always the case for us here on Earth. Okay? Practice problem. Radio signal from a galaxy is measured having a frequency. Use that previous equation, which was this. Let me pause the recording. Resonance. What is resonance? What do you remember from it? We've talked about it some with the bridge and stuff.
natural wavelength.
The input frequency, or the outside, yeah. And what happens when those two frequencies match up? Constructive interference, which means the amplitude increases. That's our basic idea of resonance. Increasing the amplitude of a wave by repeatedly inputting energy at the frequency of the natural resonant frequency of whatever it is that's resonating. Excellent. Swing sets we talk about, Tacoma Narrows Bridge we talked about, soldiers marching on bridges I think we talked about, Mexico City earthquake we might have talked about. Okay. So that's the general idea of resonance. It's used all the time in sound because almost every musical instrument you've ever heard deals with resonance in one way or another. It's the reason why guitars and violins and cellos have bodies. That's why wind instruments have tubes to resonate at a certain frequency. The other concept that's going to come up a lot with sound and resonance is the idea of a standing wave. We've talked about waves traveling through a medium, moving energy from point A to point B through a medium. A standing wave is formed when waves in opposite directions interfere with one another in such a way, when they have the same speed and same wavelength and they interfere, they will create a wave that no longer appears to be moving from one point to another point. It appears to be standing still. That doesn't mean that doesn't mean that the material isn't moving. It just means that the waveform is stationary and you still get some oscillations standing in place. When a standing wave happens, there's no energy being transferred anymore from point A to point B. The energy is standing still, being stored either as potential energy or kinetic energy of the medium. Okay, and that will be varying back and forth from potential energy to kinetic energy, back and forth, just like simple harmonic motion. And you create these things that we've talked about before called nodes and antinodes. Nodes are regions where the material is no longer oscillating at all. Antinodes are where the amplitude is very great, and everything in between. So, okay, so standing wave. Standing wave, there's a standing wave. Don't do that. Bad. Okay. Here's a, what, see? Standing wave. Okay. Standing waves in a string are where we're going to start. But when we talk about standing waves in resonance in music, we talk about stringed instruments or string standing waves, and then we move into air columns. But they're very similar, okay? So here's what we just did. Standing wave on a fixed string that's fixed at both ends so it cannot move. That means the nodes, you have to have nodes at the ends in order for these standing waves to occur. The first standing wave that can occur is when the string is half of a wavelength long. You get regions of extreme motion, those are called antinodes. You get regions of no motion, those are called nodes. And this is known as the fundamental, or the first harmonic. The second harmonic will occur on the same string, but at a different frequency, where the wave is exactly, the wavelength of the wave is exactly the length of the string. This one is going to have a frequency twice as much as this one, as the fundamental. I've doubled the frequency of the wave, I get the second harmonic. The third harmonic is going to have a frequency 3 times the fundamental. How many waves are on that string? Or what's the wavelength that's there? 1.5. The string is now 1.5 wavelengths long. Okay? This is an actual diagram of it, and here is, these are a little bit more cleaner drawings than those last pictures. Does that idea kind of make sense? Okay? When you pluck a guitar string, or a violin string, or a cello string, you set it into vibrations, and you actually set it into like an infinite number of vibrations. Most of those vibrations instantly cancel themselves out. When they reflect off the ends, they die away. The vibrations that remain are the ones that resonate at that particular length of string and at that particular wave speed. So you get resonance happening at all these frequencies, and that's what makes the sounds you hear when you pluck a string. Let's look at resonance and how we'll do math and calculations with it. You guys recognize in your data book that there are no equations for resonators, open tube and closed tube resonators. You just have to remember what can fit on the string or what can fit in the tube in terms of wavelength, and then deal with velocity equals wavelength times frequency. And that's the basic setup. So here, and don't worry so much about the stuff on the right, look mostly at the stuff on the left. Here is an open tube resonator, open at both ends, so the wave you'll basically end up with very similar to what we just dealt with a string. The fundamental mode of resonance is going to happen when the wave inside the tube is half of a wavelength of, the tube length is half of the wavelength long. So that's what this right over here says. The length of the tube is half of a wavelength. If I combine that with the equation velocity equals wavelength times frequency, I will find the frequency of the wave is v over 2L. Okay? We're assuming that all these waves are moving through the same medium, so their velocities are all the same. The next harmonic, the second harmonic that can happen is when the wave exactly fits in the tube. Notice that I've gone from half a wavelength to a whole wavelength. The next harmonic will be at 3/2 of a wavelength. So for an open tube resonator or for a string, the harmonics occur on n over 2 wavelengths, where n is an integer. 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, and so on and so on. You get all the harmonics. Does that make sense? Yeah? Notice that the frequencies are easy with harmonics because you get a fundamental frequency, which you can calculate if you know the length of the tube or the speed or whatever. The second harmonic is just 2 times that frequency. The third harmonic is 3 times that frequency, and so on and so on and so on. So the frequencies are really easy for strings and open tube resonators. A closed pipe resonator, slightly different. Slightly different in that, notice now that what happens is you get a node on one end and an antinode on the other end. Rather than having nodes or antinodes at either end, you have one on the other. So this first fundamental resonant frequency happens when the wave is only 1/4 of the wave inside of the tube, or the tube is 1/4 of a wavelength long. Okay? So for the fundamental on a closed pipe, or a pipe that's closed at one end, you get 1/4 of a wavelength for the fundamental. They call it the third harmonic, but it's really the next harmonic that will happens when 3/4 of the wave is within the tube, and then 5/4, and so on and so on and so on. So here, when you have a pipe that's closed at one end, you have n over 4 wavelengths, where n is an odd integer now, 1, 3, 5, 7, 9. Okay, it doesn't work, it doesn't fit, right. And then to get our frequencies, instead of it being every integer, you get our fundamental frequency, and then the next harmonic is 3 times that, the next harmonic is 5 times that, and 7 times it, and so on. Okay? Closed pipe resonator is a little bit more challenging just because you're dealing with a 1/4 wavelength instead of that starting it right at a 1/2 wavelength, but that's kind of how it all fits. Got some websites here that can help you see standing waves a little bit better, and you can play with those a little bit when you get a chance.